Good morning to everyone here. It's been over the last 30 years. Professor, I'm Sharma. Professor Sharma, a great motivator, a brilliant academician and teacher and innovator and promoter of best practices within the chemical industry here and abroad. Professor Sharma comes with a brilliant background in chemical engineering with his PhD from Cambridge, followed by a long stint at ICT, Indian Institute of Chemical Technology in Mumbai. He has been recipient of several awards over the years, including India's biggest civilian awards, Padma Bhushan and Padma Vibhushan, and also been honored with several awards by international bodies like Royal Society of Chemistry and Institute of Chemical Engineers with Moulton and Leverum Award. He has guided several PhD students and guided several companies in India to look at within the organization how to convert one of his favorite themes, the first one being selectivity engineering and the second one being how to turn liabilities into assets. And a great pleasure in asking Professor Sharma to share his vision and strategies that we could adopt in the future. Professor Sharma?
To give you a tour of the horizon and explain to you that right from the beginning of chemical industry there was a penchant for cleaner and greener technology. And I'll take you back almost to the birth of chemical industry, and one of the most legendary things that happened in England was how the Leblanc process by reduction with carbonation from the flue gas. There was a famous incidence of His Majesty's Alkali Inspector, sulfuric acid per capita, and how the dirty lead chamber process was replaced by contact process, the first important vapor phase catalytic process for which we still see improvement. We still see improvements in the Solvay process, so much so that we call it Solvay clusters. Then you see the famous caustic soda, that how one operated with diaphragm cells and how this asbestos diaphragm was improved. But before that happened, caustic soda was made by causticization of soda ash because the same plant also had lime. How this got replaced by mercury cell, then one found that mercury was the most undesirable thing, and famous case in Manitoba, and this got replaced by membrane cell, and membrane cell has seen further improvement with not only catalyzed anode but also now internal fuel cell, so that energy consumption comes down very, very substantially. So compared to the mercury process, we now have membrane process so clean, and a triumph in the world of creating membranes based on nephron, originally from the space program. Now, industry itself is an outstanding example of converting liability into an asset. Why? How will you dispose these raw hides? And converting raw hides into leather, where we have had outstanding success in not only chromium exhaustion, now almost to extinction, because chromium discharge was a very serious problem and plants were ordered to be closed, and now we have replacement for chromium. And how high solid paints are making a big impact. The solvent base have been replaced by emulsion paints. In fact, part of the vocabulary of a common man, that how you use emulsion paints. The other thing I want to tell you is that when you have harsh processes, I want to remind you that Germany prospered on rapid chemistry. Everything that you could think of was based on acetylene, vinyl acetate, vinyl chloride, chloroprene, name it. Even ethylene was made from acetylene hydrogenation. Practically all of it is completely displaced because acetylene is inexpensive, but was an outstanding example of how an inorganic chemical, calcium carbide, gave birth to organic chemical industry, and we have now much cleaner. Now these were very dangerous processes because in presence of copper acetylide can detonate. So you should see that how we have been able to replace the acetylene based processes to much neater, cleaner processes. Now I give you an example of how oleum or SO3 was used to remove, say, benzene from hexane to make it food grade. You will see that is a harsh process. And how do you dispose that aromatic sulfonic acid? What do you do with the waste sulfuric acid? This is completely replaced by extractive distillation. So you see a dirty process being replaced by a clean process. Nitrobenzene reduction, you know, aniline was one of the prime starting molecule like phenol, aniline. And aniline was all made by nitrobenzene reduction with iron and acid. You will realize that this is a very dirty process and was completely replaced by catalytic hydrogenation both in liquid phase as well as vapor phase. Both are industrially practiced. But prior to that, cyanamide was able to convert the chemical into pigment grade iron oxide pigment, and they made more money from iron oxide pigment. The message is that if you can't replace and do value addition. Now this has been going on all along, and I give you two examples how ferrous sulfate, iron sulfate that comes in making titanium dioxide by the sulfuric acid based process, Chemira, has very large scale plant for polyferric sulfate as coagulant. So here is an item of liability you convert into a useful product. Later I'll explain to you how field class processes were done with aluminium chloride and how this aluminium chloride was valorized into polyaluminum chloride as a coagulant in water treatment. That it has come to such a stage today that many of these field craft processes have been replaced with zeolites, and people now deliberately manufacture polyaluminum chloride, including few plants in India. Nitric acid, as you know, from ammonia preceded synthetic ammonia. And that NOx emission, because it is colored, one could witness it. And how this is converted to an acid, I'll explain to you in very shortly. But what was done, that you absorb N2O4 from NO2 in high pressure system. This was one of the classic cases of a molecular reaction, and the volume of the reactor will go down by 10 raised to 3, that means 1000 times. And this was a great achievement because we had drastic reduction in the net consumption of stainless steel. I would like to give you this outstanding example of how a serious liability is one of the biggest assets today, and that is how H2S is valorized into sulfur. You might remember that in 60s, even 70s, the sour gas that came along with production of crude oil in Middle East, all of it was flared. So a lot of SO2 was going into atmosphere. Nothing of the kind today exists. All H2S is converted to sulfur, and major part of the sulfur today, I would hazard a guess more than 95%, if not close to 100%, is from sulfur recovery from H2S, either from sour gas or from hydrodesulfurization of diesel or gasoline. And the great advance that took place, just like in sulfuric acid, the double contact, double absorption resulted in SO2 emissions below 300 ppm, which used to be earlier as high as 5000 ppm. And the catalyst development in the cross process, now the emission of sulfur containing compound is next to negligible, because even that vent gas goes through a liquid phase process to convert into sulfur. I'm trying to impress upon you that this is not a recent phenomenon, that green chemistry, but it's become now very fashionable to invoke that, and it is very helpful because invoke the word green, money pours in, you get projects by under the name of green chemistry, and people pretend that this process is green. I have known many examples of this kind, and then when you dig it into it, you find that it's not green. So this sulfur part I have already mentioned to you that how. Now, when carbide-based processes were operational, it was possible to valorize that good quality calcium hydroxide into precipitated calcium carbonate. If nothing else, at least could be used for cement industry. Now, all I'm trying to say is everywhere, don't treat any product as a waste stream. It is a raw material with negative cost. And I can give you up to examples of practice where I have had hands-on experience. Now take this NOx. I told you it is colored, so everybody can witness that you are having emission, and everybody knows that NOx are very bad. And by very elaborate simulations, a number of such plants exist in India today, where NOx either from nitric acid plant or from nitric acid based oxidations. Whenever nitric based oxidation cannot be replaced by air oxidation, you will always get NOx. Unfortunately, you also get N2O. So the breakthrough that came in N2O dealing, two types of breakthroughs came in. One is that you developed a catalyst which decomposes N2O into harmless nitrogen. The other one was this breakthrough by Russians as well as Monsanto, where you could react benzene with N2O to give you phenol. To best of my knowledge, it is not commercialized, but it is a viable option when N2O, for example, making adipic acid, you still do nitric acid oxidation of cyclohexanol, hexanone mixture. Now this NOx, I'll explain to you how it is valorized into very high percentage sodium nitrite, and you will get a flavor of this, that we do this elaborate simulation, and all that was required, which will surprise many of you, you have to only change the operating conditions for this gas to be scrubbed in caustic soda, and you improve the selectivity to nitrite, because you need nitrite for diazotization. Number of processes in the dyestuff industry still critically depend upon diazotization, and we were able to get 95% plus selectivity to sodium nitrate, and a number of commercial plants operating. Here was the liability of brown fumes going out, and you have converted them into value-added products. I alluded about this Friedel-Crafts process. Two things happened. First is, when ethyl benzene was all made by Friedel-Crafts, is now completely replaced by zeolites. Even cumene was made by aluminum chloride, subsequently phosphoric acid, kieselguhr, and now zeolites. But this aluminum chloride earlier was valorized into polyaluminum chloride, and now, as I said earlier, you commercially manufacture polyaluminum chloride. Few plants in India for chlorine utilization make polyaluminum chloride. So, but there are still number of processes where we have not been able to replace Friedel-Crafts. So the message is, please do valorize that aluminum chloride into polyaluminum chloride. Number of processes in dyestuff industry, perfumery industry still depend upon Friedel-Crafts process, because we have not been able to replace these Friedel-Crafts processes even with best of the zeolites. Here's another example. Now in metaphenoxybenzaldehyde, it's all done by a dirty process, not a clean process at all. Whereas you can have it as a very clean process as indicated to you, because we can get metaphenoxytoluene by the cross reaction between metacresol and phenol, and then you could do the liquid phase oxidation. Now, here is another instance of how to marry two, I don't call anything as byproduct, I prefer to call them co-products. You all know that in pentoethitol, trimethylol propane, you all get sodium formate. Now sodium formate, and in all sulfonations of aromatic substances, alkali fusion, you get sodium sulfide, like in manufacture of resorcinol. Earlier, it used to be the case even for phenol. Now, this sodium sulfide was married with sodium formate to make sodium hydrosulfide. So, you see, two unwanted products combined to give you a very high value-added product, sodium Na2S2O4. And this is commercially practiced, including in India. All I want to say again and again, now this was another classic example, that when vinyl chloride made from EDC, ethyl dichloride, that HCl was a source of nuisance, and then oxychlorination process was developed. And people have forgotten that first time oxychlorination was developed by Dow, because they were making phenol from chlorobenzene by high pressure alkaline hydrolysis, and they needed to develop that HCl utilization. So they had done work on oxychlorination of benzene with HCl. That really didn't get commercialized, because by that time the benzene sulfonation route, benzene chlorination route was completely replaced by cumene-based phenol, a very neat process in late 50s. But this oxychlorination made a huge difference to this large-scale PVC manufacture, which is in millions and millions of tons. And most people now have this oxychlorination. The polychlorinated products that came, how to valorize them? Now, you burn them and scrub HCl and use HCl for other purposes. But here was a very interesting development of chlorinolysis of this polychlorinated compound. Companies like Hex practiced it, and you get carbon tetrachloride and perchloroethylene, very value-added chemicals. Of course, today the story is a bit different, that you don't want carbon tetrachloride as a solvent because of the health hazards. But I will explain to you something which we did. It's some element of something unusual. On face of it, people, if you ask a graduate student, can this happen? I'm going to explain to you that when you make the epichlorohydrin from allyl chloride, chlorine, water, you end up in getting trichloropropane because there is a finite solubility of chlorine in water. What we did was, and which is, I say, contrary to the wisdom, you scrub chlorine in hot caustic soda, and contrary to what you will think, we could strip out HCl. And this was done with very simple experiments in the lab, and this gives you pictorial depiction of how it's a problem in mass transfer, that if you can strip out HCl faster than it goes into the bulk, you succeed. Believe me, you can get almost 80% selectivity, you get pure HClO. And pure HClO when reacted with allyl chloride, there is no question of trichloropropane coming. I am pleased to tell you that this is today commercially practiced, and centrifugal absorbers are used which have high values of liquid side mass transfer coefficient and very high values of gas side mass transfer coefficient. Very large scale plant exists, and now the only fundamental paper in the literature is what we had published a long time ago with my collaborators, the present director of ICT, G.G. Yadav. We did this work. Here is the question of, again, in a very neat way, using principles of chemical engineering to convert liability into an asset. Now, one of the most outstanding example of a dirty process being converted to clean process is ethylene oxide, ethylene glycol. All of it was done by chlorohydrin process. And when in 1930s direct oxidation of ethylene to oxidane, that is ethylene oxide, came in, it was a fantastic breakthrough, a major breakthrough. And at that time, compared to theory, the yield was as low as 60%. The science of catalysis, which has been developed over the years, today it is more than so-called theoretical. There is some peculiar theory behind it, but we are close to 84-85%. Substantial reduction in CO2, increase in capacity because each mole of CO2 carries 94 kilocalories with it. So you have heat transfer problems which are taken care of. These chlorohydrin plants were then inherited to make propylene chlorohydrin propylene oxide. And look at the fantastic development in making propylene oxide, which goes for propylene glycol and polyol, that since one couldn't do direct oxidation of propylene because of allylic effect, that you will get acrolein rather than propylene oxide. Although much research is going on in the recent past, whether we can do direct oxidation of propylene to propylene oxide. But if you couldn't do direct, why not something indirect? And that oxidation with ethyl benzene hydroperoxide or tertiary butyl hydroperoxide and valorizing co-product made a big impact on manufacture of propylene oxide, propylene glycol, polyol. And the latest, which is the cleanest because there is no co-product, is propylene plus hydrogen peroxide going to propylene oxide, for which large-scale plants exist. Now here is an outstanding example, first starting with the oxide ethylene glycol, now with propylene oxide, propylene glycol, polyol, where you have very neat process. Hydrogen peroxide is Mr. Clean. What it leaves behind is only water. So we keep on going through these substitution bromination reaction which people do with bromine, then HBr comes out. there is a neat solution. You do it with bromine chloride. Or you will do in a biphasic system that in situ HBr is oxidized with hydrogen peroxide to bromine, goes back into the organic phase. That means you can have 100% utilization of bromine for bromination, where bromination reactions are very important. Now, a lot of benzaldehyde is made from toluene. So is benzyl alcohol via chlorination. Monochlorination, side chain chlorination gives you benzyl chloride, benzyl alcohol. Dichlorination gives you benzyl chloride, benzaldehyde. But all these can be made by a neat process of converting, doing direct liquid phase oxidation of toluene to benzyl alcohol, benzaldehyde. And benzoic acid is always made by liquid phase oxidation of toluene. Anthraquinone, in dyestuff industry, in wet dyes, anthraquinone is an indispensable. So also in paper industry. We have not been able to find a replacement for Friedel-Crafts process. Still, you need stoichiometric amounts of aluminum chloride to react benzene with phthalic anhydride. But there is an alternate process, one based on direct oxidation of anthracene, not using inorganic oxidizing agents, but doing plain oxidation. But anthracene is in short supply because coal tar industry doesn't grow much because there are breakthroughs in steel industry. But there is this neat process making use of these other process, naphthaquinone with butadiene and oxidizing that material. There is a commercial plant. See how neat it is. You have 100% yield in the reaction of butadiene with naphthaquinone. Now the naphthaquinone, as you know, when phthalic anhydride was made from naphthalene, that itself is a very neat example of green chemistry. Naphthalene is 10 carbon atoms, 2 carbon atoms were going to carbon dioxide. When it was converted to orthoxylene, it meant a cleaner process, no CO2 emission, comparable to naphthalene going with 2 carbon atoms, definitely going to carbon dioxide. Or benzene going to malic anhydride, 2 carbon atoms going to carbon dioxide, completely replaced by butane oxidation to malic anhydride. I consider that as one of the major breakthroughs in the recent past, in the last 15-20 years in the organic chemical industry. So here again you have a process which is clean, very clean. Now in perfumery, bulk, one of the important bulk perfumery chemical, synthetic rose, is phenylethyl alcohol. Again, Friedel-Crafts process was considered to be indispensable because you react benzene with ethylene oxide and stoichiometric amounts of aluminum chloride. But you can certainly replace this, and there are plants of styrene oxide, that too with hydrogen peroxide. You don't need peracetic acid, and hydrogenate that directly to phenylethyl alcohol. But also allows you to make phenyl acetaldehyde, which is also a perfumery molecule. Now I come to this diphenyl oxide, which was, I need to give a little story. When Dow was operating their phenol from chlorobenzene, they had this byproduct. They had 2 byproducts from chlorobenzene to phenol, the diphenyl oxide and phenylphenols. There is a simple chemistry to explain how it comes in chlorobenzene alkyl hydrolysis. And they valorized both these products, and diphenyl oxide ended up in one of the most outstanding heat transfer, Dow-Thumb, which is a eutectic mixture of diphenyl oxide and diphenyl. And diphenyl was coming as a byproduct in toluene to benzene, when toluene was in great surplus, and that is all gone. Toluene is not in great surplus. And one could do neat vapor phase dehydration. There is a plant in India, in Algeria, where diphenyl oxide is made by vapor phase catalytic dehydration. There was used to be a plant in ICI in UK. There was also a plant by Dow later on when they displaced. The demand for diphenyl oxide became so great and chlorobenzene process was completely displaced. You had to deliberately manufacture this. You have to deliberately manufacture phenylphenols, ortho as well as para. Paraminophenol, which goes for paracetamol, very well-known anti-inflammatory analgesic compound. You can make it by a very neat process from nitrobenzene by catalytic reduction, and not from nitrochlorobenzene or nitrosation of phenol. How hazardous chemicals can be replaced, and one of the most outstanding example practiced in India, that how you could make the well-known viricide isoproteron. Other chemicals did this. without using phosgene from urea and ammonia from para-humidity. And this technology of using urea and amine is also exploited for isophorone-diamine to isophorone diisocyanate. It's a very interesting development that you can replace phosgene use by completely safer process, or much safer process doing that. And examples after examples of this kind I can keep on reading out ad nauseum. Let's say the chromium compounds in water treatment. Water treatment is a very big business. And in coming years, one of the major market for water treatment chemicals would be in the shale gas, fracking. Water recycle is crucial for shale gas, and we'll see further breakthroughs in using very benign molecules for water treatment. The chromium is now a thing of past, that one doesn't use this in water treatment at all. Now, high pressure, very high pressure technology to be replaced by low pressure. This is also an example of equivalent of a cleaner and greener process. Remember how low density polyethylene was made at pressures exceeding 1000 bar. That how LLDP could be done at 30, 40, 50 atmosphere. How high density polyethylene is at a low pressure. But the most outstanding example I want to give you is carbonylation of methanol. When BASF first commercialized this was on cobalt-based technology, 600 bar. When the plant was commissioned, the homogeneous catalyzed methanol carbonylation became a success and a brand new plant became redundant. Just as the brand new plant of ICI making nitrile from acetylene plus SCM was overnight replaced by propylene ammoxidation. And how acrylic acid manufacture from propylene or methacrylic acid. They are outstanding examples of cleaner and greener processes. And what I want to tell you is that every time there is a co-product, think of that for value-added products. So I give you flair for some examples. In the ethyl benzene manufacture, diethyl benzene came in. And this diethyl benzene then was valorized in process akin to styrene from ethyl benzene to divinyl benzene, which is indispensable in making ion exchange resins for water treatment as well as the cationic ion exchange resins or anionic ion exchange. So divinyl benzene is used for cross-linking, all made from the core product diethyl benzene that came in. The manufacture of para-diethyl benzene for requiring for paraxylene plant is a different story, but I am talking about byproduct. And how when toluene was in surplus, toluene was being disproportionated to benzene and xylene, or now you disproportionate toluene with C9 aromatics and make more. So there is nothing like anything being unwanted. You have to depend on your ingenuity to keep on making more valuable. These stoichiometric reducing agents which are used, particularly Na2S, it's a dirty process to reduce aromatic nitro compound. You end up with thiosulfate which has a high COD. Then you valorize thiosulfate for merchant sale in paper industry. Thousands of tons of thiosulfate are recovered in India in making sulfur black, and that is used in paper industry. You don't discharge this negative chemical is converted to a very positive chemical. Just as I gave you example of H2S to sulfur, and whenever H2S comes out of a process, you scrub that in caustic soda, sodium sulfide has many industrial uses other than that. All these stoichiometric reagents for aromatic nitro compounds, by and large, most of them have now been replaced by catalytic reduction with hydrogen. Now, since you cannot defy the rules of so-called thermodynamics when you do chlorination, nitration, you want para-product more selectively. Unfortunately, you land with a lot of ortho. Find more uses for ortho. And the classical case for nitration of toluene, where all ONT, orthonitrotoluene, could be converted to TNT. But if you can increase the yield of para-nitrotoluene by using zeolites or para-chlorotoluene by using zeolites, it will improve the economics of your process. And para-chlorotoluene is commercial using zeolites for chlorination. In chlorination you use zeolites and you get more para. Now, I'll give you some examples of how co-products are valorized. In a phenol plant, even with best of the efficiencies, you get acetophenone and alpha-methylstyrene. Instead of hydrogenating alpha-methylstyrene and recycling, recover this. This is being done in India. And this alpha-methylstyrene is a fantastic material because dimer of this is used in industry, high-value added product. Para-cumulphenol is the terminating agent for polycarbonate in GE, now SABI. And therefore you get, and to make cumulphenol, you don't even need pure alpha-methylstyrene. And most recently I heard that there is a large-scale plant being put up for alpha-methylstyrene acrylonitrile copolymer. The ingenuity of chemistry, chemical engineering, chemical technology is such that you can think of value-added products from so-called waste stream. Let me deviate a little bit from PowerPoint presentation. Professor Sheldon has been talking about this large ballast that you get in API manufacture, 10 kilos to 50 kilos. It's a reality. Why treat them as waste and deal with doing incinerations and all? And I single out nitrogen-containing compounds and refractory molecules, like aromatic sulfonic acids. Now, you know, there is a big problem of nitrogen-containing compound, both organic as well as inorganic. And I dare tell you that all these, from morphine to piperazine to tertiary butylamine and all in the pharmaceutical industry, they are all being recovered and major part of it is being recycled right within the API industry in India commercially. Now here is an example which I already given you about alpha-methylstyrene, but I deviated. I told you that I wanted to tell you something about particularly, but I want to remind you once again how this nitrogen containing compound, and take you back to my favorite Solvay process. Please remember, Solvay process came into existence when synthetic ammonia was not there. Synthetic ammonia came in 1910s. So the efficient utilization of ammonia was absolute necessity for Solvay soda ash process. So neat was this ammonium chloride conversion to ammonia, both through chemical engineering and very simple reaction with lime, that the net consumption of ammonia in a soda ash plant was only 2 kilos, 2.5 kilos per ton of soda ash. So if it could be practiced in 1860, why discharge any ammonium salt in the form of ammonium chloride, ammonium sulfate, and put up with the headache of nitrogen emission? Aromatic substances like pyridine are much easier to recover from waste streams. You need a change in the mindset, and it's being done. It is here where the management support is total. Unlike totally new processes, recovery of chemicals from the waste stream and making processes cleaner, you get full support from the management, therefore implementation becomes much easier. You don't have Mr. Nose there because you know that you are converting a liability into an asset. Now, I give you another flair. Rani nickel is an outstanding catalyst for hydrogenation, and many times you do this along with zeolite because you want some unwanted thing to be absorbed by zeolite in an API industry. And how do you recycle this Rani nickel? Because the Rani nickel manufacturer doesn't want to buy containing zeolite. There was a very simple solution that you recover Rani nickel magnetically because it's magnetic, and you have converted a liability into an asset. I'm giving you live examples. Now, polymeric substances, this is a big problem these days, how to get rid of polyethylene, polypropylene, polymethyl methacrylate, polycarbonate. There is a way, now polymethyl methacrylate is easy to depolymerize. It's easy, even polyester completely recyclable, and these technologies are now being practiced. I can keep on giving you, now I'll give you some flavor for more engineering oriented. How continuous processes can make a big difference. And fortunately, OPRD has been giving many examples, including a very recent paper, how converting batch process into continuous process. I'll just take you two simple examples. One is nitration. You know nitrations are hazardous. And converting a batch process into continuous process for specialty chemicals also makes a lot of sense. You want to do fluorinations. You want to do reactions with isomethane. You will find continuous processes are very, and the pharma industry, after a lot of reluctance, is now moving. Globally they are moving. In India also they are threshold of moving into continuous processes where wherever you don't want inventory, where there are hazards, doing ozonolysis and things like that. Here's an example that a byproduct that comes in making isophorone, you would have burned this material, but this was valorized into a base stock for making joss sticks, agarbattis, and this is sort of was commercially practiced. Now, this was the most outstanding development by Monsanto, although the original fundamental paper came from NCL by Iyengar, that you can do aerobic coupling of nitrobenzene with aniline using a phase transfer catalyst. This replaced for making number of rubber chemicals by a dirty process based on nitrochlorobenzene. And this revolutionized making the corresponding compounds. Here is an example of how breakthrough. So good was this piece of work after the first paper in Tetrahedral Letters that the paper from Monsanto came in JACS, that this was a novel breakthrough in making, and process became cheaper and cleaner. Here is another outstanding example. The greatest ever success in agrochemical was glyphosate. At one time, for several years, 40% of Monsanto came from glyphosate. There is no molecule in the history of organic molecules and agrochemicals so simple a molecule and so effective a molecule. But this was made by a dirty process. Till a very neat process was developed for immunodiacetic acid by conversion of diethanolamine with Rennie copper and hydrogen as a co-product. Just see, material of construction giving way. We have ways and means of getting over this problem, and number of processes now make use of this. Then, I'll skip this. I'll give a somewhat more, I'll skip this one. This was a very interesting example in Atelier, where diacetone alcohol was made by a classic process where sodium ethoxide was, sodium was recovered through phosphoric acid treatment, giving serious problems in crystallization, shutdowns in the plant. An ion exchange process was adopted. Plant capacity went up by, Rajiv Pandya is here, he is witness to this. Plant capacity went up by a factor of 3, and no effluent were the name. See, when you talk of something which is practiced, I presume it has a greater penetration in the minds of participants than you only keep on theorizing and saying this can be done, that can be done. You have number of processes where you do steam distillation. Let me give you one or two examples. Nitrotoluene in water. Now, steam stripping from engineering point of view, now people get initially scared that I have only 3000 ppm of this refractory molecule, particularly nitrogen containing aromatic substance like nitrotoluene, nitrobenzene. And you can do solvent extraction, but you can also do steam stripping. The first reaction of anybody would be uninitiated into this thermodynamics of this highly non-ideal system. They would think that 0.3% of material will require such large quantity of steam that you will be going fat. But they don't realize this non-ideal behavior ends up in steam consumption so low that a lot of steam stripping is done on a grand scale in industry of these molecules. Sometimes you can do, if it is acidic or basic, through use of ion exchange resins. You can also do solvent extraction. All these are practiced in India. For example, in 2,4-D manufacture, 2,4-dichlorophenoxyacetic acid, although present at 500 to 1000 ppm is bad for discharge, but can be, there is a value in recovering and recycling in the plant. Now, every time you have this problem, please look. Now, if we were removing nitrotoluene by steam stripping from that organic mass, why not use short part distillation to recover nitrotoluene right there rather than doing steam distillation, then recovering from there, then the water quantity containing dissolved nitrotoluene to be recovered? And short part distillation has been a great success in this kind of recovery. Energy consumption comes down drastically. Another real breakthrough is coming through membrane separation. This nanofiltration is a great boon. That any molecule with molecular weight more than 250, and most of the APIs, and with the development in polymer science and technology, where you have now solvent resistant membranes including for DMF and DMAC. isopropanol and all this, very easy to handle, and these membranes are commercially available. So we are converting a lot of these processes into neat processes using nanofiltration. And number of these nanofiltration membranes are now used in India, apart from RO being used to remove coloring material from textiles and all. And this means neat process, your process efficiency goes up, solvent recoveries become better. So nanofiltration has been a great success in the chemical industry. Solvent extraction can be used, but nanofiltration is the simplest of the. Now vent streams which carry over organic substances. Now water pollution people are able to track. A lot of people get away with air pollution. But these can be subjected to using fine engineering practices, value addition. I'll give you two illustrations. One is some reaction being conducted at minus 70 degrees with direct injection of liquid nitrogen. Now even at minus 20 there is significant vapor pressure of methylene chloride, and then you emit nitrogen containing methylene chloride. Just convert this into indirect cooling with a coil and all your methylene chloride is safe. It's done commercially. So like that we can keep on giving examples. And I think burning problem in India and elsewhere in the world is utilization of bagasse in India, because bagasse is only agro waste available in large quantities practically throughout the country. This is not a forum for me to dwell upon this subject, but bagasse valorization is a big thing to be done. We did some work on phase transfer catalysis and converted some of the processes like making triphenyl phosphate, trichlorophosphate phosphate by a very neat process using phase transfer catalysis, and also not using quaternary compound but polyethylene glycol 400 as a phase transfer catalyst, because even if you have small discharge of polyethylene glycol, it is treatable, unlike quaternary compound for which there is a very strict specification in the discharge. This is also commercially practiced in India. But one of the things we have done, which is very unusual, recovering these phenolic substances from waste stream using phase transfer catalysis is one of the rare examples in adoption of phase transfer catalysis for substances going in waste streams to be recovered. This audience may not be much interested in the continuous part. I already explained to you. This I'll skip because there is something in. How biocatalytic processes can make a big difference in terms of ballast that you throw out. This is one neat example in the penicillin series that how a biocatalytic process made such a difference. So what I'm saying is there is merit in looking at this. There is also a lot of merit in looking at biphasic processes. We were able to make 2 degree, 3 degree amides into the isocyanates using Hoffman reaction and not using phosgene at all. And this is also commercially practiced. Electrochemical processes are very neat. Nothing is neater than electrons. So whenever you can't do by any other, you do electrochemical process. And BSF is one of the great practitioners where methoxytoluene is converted to anisec aldehyde with concurrent reduction of phthalic anhydride to phthalate. So electrochemical processes need attention because they are very clean processes. Many examples can be given, ease of scale up with the kind of material of construction and all that. Ladies and gentlemen, one of my objects of presentation was to explain to you that from the beginning there has been a penchant for cleaner processes. I gave you a flavor, many examples, not a recent phenomenon. But it's a very catch-on phenomenon these days, and academics love it because you invoke the word green chemistry, they think money will pour in. I was heading a committee in 3 years, we couldn't support one single project because they're all pretentious in having a cleaner process. You have to demonstrate it is really clean and there is money in it, because unless the process is clean and makes money, nobody is going to buy it. It's just like people are talking of renewable raw materials, have forgotten their entire DuPont empire was based on furfural. Entire Union Carbide initial as a feedstock. 55 products were made from alcohol by Union Carbide. India started with alcohol as a feedstock. All of them are shut. Acetic acid, ethylene, nothing of kind works from alcohol in view of the economics. You may say renewable raw material. Same way, what we found that one area where this cleaning of the processes, where you see improvement in yield and recovery from waste streams, clicks very well with the management. Once you have a penetration, because ultimately decisions are taken by board of directors, and board of directors don't have much feel for this science-based industry. Very few boards in India, board of directors really know the depth of chemical industry and the science behind it. Having sat on many boards, I can tell you with some degree of confidence, and I'm willing to take on people who want to criticize this, and I'll give them live examples of how board dealt with many matters and how wrong they were. Thank you profusely for giving me a hearing, and I hope I have enthused you that cleaner and greener is smarter, and liabilities can be converted into assets. Thank you.
Questions, if there are any. Anyone?
You said that
I'm not even in this practice.
I know, but how it
Even used as a slurry, although some trickle bed reactors based on pelleted uranium nickel are being attempted, but bulk of the uranium nickel based hydrogenations are in slurry reactors. And you have one of the earliest practitioners of this was ICI. They had online magnetic separation as the slurry came out for nickel to be removed and recycled. And you can easily get it, highly magnetic, so you can easy. Same thing about cobalt. See, of course, let me give the history, how hydrogen was made by electrolysis of water. Then, the recent example of HCl, apart from oxychlorination, HCl is now commercially electrolyzed to give hydrogen and chlorine by fire. Aluminium is electrochemical, caustic soda is electrochemical. But in the organic part, first major breakthrough was Monsanto's process of electrodimerization of acrylonitrile to acrylonitrile. That I thought was a major breakthrough in the history of now there are many processes that I explained to you where people were using directly or indirectly. Suppose you are using chromic and there is no process other than chromic. Then the chromous electrochemically is converted back to chromic and completely recycled. Hicks had Montano wax where this was done. The methoxytoluene to be converted to acetic aldehyde is commercially practiced by BSF. But wonderful thing they have done, you have anodic as well as cathodic process going on simultaneously, and phthalic anhydride is converted to phthalate. Now there are many other, I can give you reel out many organic processes which are commercially practiced by electrochemical, because there is a clean maritime.
Things have been committed to since a long time. Sustainability as well as green chemistry. It's just that green chemistry is a new name that has been given recently, and I want to take this opportunity to have Dr. Raj Gopal facilitate and honor Dr. Sharma. We are giving a kind of a certificate where 10 trees have been planted in the name of Professor Sharma at a location in Odisha. So all our speakers across the 3 days of conference, now time and being here.